what we're going to do is we want to try and figure out what, we'll try and solve our equations for the shape of an orbit. So let me draw our orbit again. And again, if we have some arbitrary point here and we measure r at a particular angle phi, then the shape of an orbit is just r as a function of phi, right? What is r at each value of phi as we go around? Now, going back to our total energy and writing that out, that's a half dr by dt squared, which is our radial kinetic energy, plus the effective potential energy, L squared over 2r squared minus gm over r. If we're going to do anything with this, we need to recast this equation with this derivative in terms of phi instead of time t. Okay, so we can do the same chain rule trickery as we did before. So k tilde, which is dr by dt squared, we can write this as 1/2 dr by d phi times d phi by dt squared, which is just 1/2 dr by d phi times squared times d phi by dt squared. And then let's go back to our definition of L, which is just big L over m, and that is just r times v phi. Now v phi, the velocity tangential to the orbital path, is just r times omega, the frequency, or the angular frequency of the orbit. So this is equal to r squared omega, and omega itself is by definition d phi by dt. Right? Omega, the frequency, is just the number of radians per unit time. So therefore we can write d phi by dt as little l divided by r squared. Just rearranging this equation here. And that means that d phi by dt squared can be written as L squared over r to the 4, and k tilde is equal to L squared divided by 2 r to the 4 times dr by d phi squared. And the total energy is equal to L squared over 2r to the 4 times dr by d phi squared plus L squared over 2r squared minus g big M over r. Okay, now I'm going to rearrange this equation a little bit. I'm going to move these two terms over to the left-hand side of the equation to leave me with L squared over 2r to the 4 dr by d phi squared is equal to epsilon minus L squared over 2r squared plus g m over r. Now, we can define at this point a variable that's going to make our lives a little easier. So this is a differential equation, right? It's a differential equation, r as a function of, for r as a function of phi, right? It is difficult to solve because it is not a non-linear differential equation because the derivative is squared. Okay, to solve this, we would have to take the square root of this side and integrate this function, and that is tricky. So math can come to the rescue. And one thing to note is that part of the trickiness, in addition to this being squared, is that the r's here are in the denominator, and it's always trickier to deal with variables in the denominator than when they're in the numerator. What we'd like to do is get some variables in the numerator to try and make life easier. And so in order to do that, we can define a new variable called u that's equal to 1 over r. Right? So then whenever r is in the denominator, and we substitute in for u will end up in the numerator. We need to also substitute it in here, so we need to know what du by d phi is. Well, that's just equal to, if we differentiate this with respect to r time and multiply by dr by d phi, so by the chain rule this is equal to that. Therefore, rearranging this, dr by d phi is equal to minus 1 over u squared du by d phi. See, so what we've done here is we've multiplied both sides by minus r squared. So we've got minus r squared on this side, and minus r squared is just minus 1 over u squared from the definition of u. Okay, so now let's substitute all our r's for u's. So firstly, we have L squared over 2r to the 4. That's L squared over 2 times u to the 4. The r to the 4 becomes u to the 4 in the numerator. dr by d phi squared, well, dr by d phi is this. So dr by d phi squared, the square gets rid of the minus sign. 1 over u squared becomes 1 over u to the 4, and du by d phi becomes du by d phi squared. Okay, and then this is equal to epsilon minus L squared over 2r squared becomes L squared over 2 times u squared, and gm over r becomes gmu. So, and we see a nice thing here, this u to the 4 actually cancels that u to the 4. So we end up with L squared divided by 2 times du by d phi squared is equal to epsilon minus L squared u squared divided by 2 plus gmu. Okay, so that's got all the u's in the numerator. It's also got rid of this horrible r to the 4 term. But we've still got this nonlinear first order differential equation here. So our next trick is that one way to turn first order differential equations that are nonlinear into linear differential equations is to differentiate them. So what we can do is we can differentiate this whole thing with respect to phi. Okay. So L squared over 2 is constant. Du by d phi squared, if we differentiate that with respect to phi, we get 2. We get twice what is in the parenthesis, which is du by d phi, times the derivative of du by d phi, which is d2u by d phi squared. Epsilon is a constant, it's the total energy, so conservation of energy means that the differential of this is 0. So we get rid of that. U squared, so we've got minus L squared over 2. U squared differentiated with respect to phi is 2u du by d phi. And u differentiated with respect to phi is du by d phi. Okay. Now notice that every single term now contains du by d phi, which means we can cancel it. And we've got 2 factors of 2 there and 2 factors of 2 there, so we can cancel them. And finally, we can divide both sides by L squared, and that will cancel L squared there, and give us 1 over L squared there. So we're left just with d2u by d phi squared is equal to minus u plus gm divided by L squared. Okay, so this is the differential equation that we have to solve in general to find the shape of the orbit. We solve this for u. We then can figure out what r is, because r is just 1 divided by u. And that is, then we're done with the solution. Let's check that we get back the result we had before for the circular orbit. For the circular orbit, r is equal to u, r, which is 1 over u, is a constant. Okay, so in other words, d2u by d phi squared is 0, and from this equation here, we get u is equal to gm over L squared. Let's call this uc for the circular orbit, and rc is 1 over uc is equal to L squared over gm. This is exactly the result that we got earlier. So we get that back. The next thing we can do is a little bit of perturbation theory. We can ask what happens when we don't have a circular orbit, but we have a small perturbation on the circular orbit. So in other words, our solution isn't UC, it's UC times 1 plus something that is small, right? In perturbation theory, you're considering small perturbations to what you already know to be simple solutions. And this is valid. The Earth's orbit around the Sun is elliptical, but the extent to which it is elliptical versus a circle is small. This is also how you take into account, for example, the presence of all the other planets in the solar system when you're trying to figure out the orbits of a particular planet around the Sun. Right? So to figure out the Earth's orbit around the Sun, the dominant component of that, or the thing that dominates how the Earth behaves, is the Sun. Right? But every other planet in the solar system is also exerting a gravitational tug on the Earth, but those gravitational tugs are much, much, much smaller. So in order to figure out the true orbit of the Earth around the Sun, you could figure out, well, what is the orbit of the Earth around the Sun if the Earth and the Sun were the only things in the entire solar system? And then you find that solution, and then you add on small extra bits to take into account the gravitational tugs of the other planets. And we'll see how this pays dividends in a minute. I'm going to write the small extra bit as W, and this in general is going to be a function of phi. Right? This perturbation will depend on on where you are in the orbit. For example, if you're on a slightly elliptical orbit, then your position U or R changes with your angular position as you move slightly closer and then slightly further away from the central mass. And the key thing here is that this is a small quantity. And in mathematics and physics, a small quantity is something where you can assume that its square is practically zero, and you can forget about any terms that creep into your equations that involve this squared or this cubed and so on. Any powers higher than 1 you can neglect as unimportant. And that's the key to simplifying the equations. So if we go back to this equation here, we need to differentiate u with respect to phi. So we've got d2 u by d phi squared. That is equal to, this term here differentiates to 0 because it's constant. And so we have uc times this differentiated twice. And this is equal to minus u, so that's minus uc, let's expand this out, minus uc times w of phi. And then we have plus gm over L squared, plus gm over L squared. Okay. But wait, uc is equal to gm over L squared, which means that this term is equal to minus this term, and so these cancel. And we get just minus uc times w of phi. And this is the equation of simple harmonic motion. Okay, we have, let me rewrite it here, we have d2u by d phi squared is equal to minus uc times w of phi. Sorry, this is w. That's this term here is equal to this term here. And the UC's cancel, and we get d2w by d phi squared is equal to minus w. That's simple harmonic motion. It has a solution, for given boundary conditions of a cosine of phi, and in general minus phi 0. Where phi 0 is just the starting value of phi, the initial value of phi. Okay, and therefore our full solution is u is equal to uc into 1 plus cosine of phi minus phi 0. So we're getting back to the result that we saw before in a little bit of a hand-wavy way, looking at the energy graph. That there is this sinusoidal perturbation on the radial motion of the planet, or whatever the object is. r is equal to 1 over u. Sorry, there should be an a here. By the way, w being small means that a itself is very small. I should note that. So r is 1 over u, which is equal to 1 divided by uc into 1 plus a cosine of phi minus phi 0. Okay, this doesn't look such a nice function, 1 over 1 plus cosine, but again, we can simplify it by using the fact that that this term is very small. A, the amplitude of the sinusoidal perturbation, is small because that's what we define to be a perturbation. We can note that 1 over uc is just rc, the radius of the circular orbit, and then let's write this as 1 plus a cosine phi minus phi 0 to the minus 1. And we can expand this using the binomial theorem. It's 1 plus the coefficient times this, so that's minus a cosine of phi minus phi 0, plus, and then there'll be additional terms here. The expansion goes on. There's a term with a squared, a term with a cubed, but because a is small, all these other terms can be neglected, and we're just left with that. Okay, so in other words, this is equal to rc minus a times rc cosine of phi minus phi 0. Okay, and finally, just to check what the shape of this orbit is, let's figure out, let's suppose we want to find two important points in that we'd like to know about any orbit. The perihelion of an orbit is the point at which the object is closest to the central mass. In other words, when r is at its smallest. And when r is at its smallest, that means this term here, which we're subtracting, must be at its largest. And this is at its largest when cosine is at its largest. So in other words, when cosine of phi minus phi 0 is equal to 2 pi n. Sorry, is equal to 1, which means that phi minus phi 0 is equal to 2 pi n, because cosine is equal to 1 every time, is equal to 1 when the angle is 0, 2 pi, 4 pi, 6 pi, and so on. So n is an integer. Okay. How often does it pass through the perihelion? Well, let's rearrange this and write phi is equal to phi 0 plus 2 pi n. So that just means that if here's the central mass, and let's say this is our starting point, phi 0, okay, then it's equal to 2 pi n. Firstly, it's equal to this point at the start of the orbit, when phi is equal to phi 0. And the next point, the next time it reaches this condition here, the perihelion, it's traveled another 2 pi, which is just an entire orbit. Okay, so it's gone all the way around once and come back to here. So it's gone around 2 pi, come back to here, and it's back at its shortest point. And then it goes around again, comes back here, that's 4 pi, and it's again back to, it then meets this condition again and is back to the perihelion. So what we've discovered here is that the perihelion occurs at the same point in space every single time, right? An orbit, we say the orbit closes on itself, right? You always retrace the exact same orbital path, right? So this, what we found is that this is the orbit of an ellipse that is slightly perturbed from the circular orbit and always comes back to the closest point to the central object every time. Any deviations from this must be a result of one of two things. Either there are additional masses that we're not accounting for. So in the case of the solar system, if this is a planet, say the Earth, and this is the Sun, then there are a bunch of other planets with little tugs on this planet. And that will alter the orbit, and that may cause the orbit not to close. The second point is that we've done all this in Newtonian gravity. If Newtonian gravity is not the complete theory of gravity, then this result may not hold. Right? It seems to hold in the case for the Earth, but we're going to see in the next lecture how this differs when you take into account Einstein's upgrading of Newtonian gravity, his theory of general relativity.